right. Good afternoon, everybody. Thank you for coming. I would like to introduce Dr. Whitwell. Dr. Whitwell graduated from Cornell University with a PhD in chemistry. He worked in the industry for many years and arrived at the college in 2006 and currently serves as Associate Professor of Chemistry. Since arriving at the college and in addition to teaching, Dr. Whitwell has served on different committees, including chairing PDC, the Technology Committee, and Faculty Council, just to name a few. In addition, he was awarded the sabbatical in 2017, received the TLC travel grant in 2012, and the Garner Faculty Leadership Award in 2011. The title of his talk today is Exploring Data, Chemistry, Math, in North Carolina Wesleyan College. Without further ado, let us welcome Dr. Whitwell.
Okay, thank you, Mayor. So when Doreen asked me if I would be interested in doing a fourth Monday, it pushed me to do something sooner than I was intending to do it. But then it also let me talk about a whole bunch of things that I wouldn't have talked about anyhow. So you see on the end here, the reason that I was quick to take it up is that there were a couple of things that I've been working on that will form a small part of the talk, as it turns out, because once I decided that I was going to do Fourth Monday, I said, no, I'm going to tell you everything I've ever done with computers. And so, you know, that's all about chemistry and math. And it really is 51 years. So in 1969, I had the fortune, good or miss, to end up at a prep school in New England where I took my first chemistry course as a sophomore. And it turned out that they had a timeshare on a computer that I never saw, but it looked like this. What I saw looked like that. And we could have a few hours a day to learn about computers, and so I started to do that. Before that, this was a computer, and I still have a few, but that was basically, you know, how we did math. And I won't tell you more about what I did there, and I will just mention these as we go through, rather than telling you everything that I'm going to tell you about. So, from Berkshire School, I went to WPI in Worcester, Massachusetts, and I'd already had a little computer experience. So when I took my first official computer course, so that now they either look like this with a keyboard and a screen instead of a keyboard and a printer, or like this. And this guy punches these guys, and so this is one line of a computer program, or one line of data. And your program ends up looking like this. And some of you are probably familiar with this, but these are punch cards, and they have 80 spots on them, and some of them are reserved for different things. The actual computer, which I didn't see at that time, would have been either this IBM 360, which was very popular in the day, or this RCA Spectra 700. And so these were connected, and these were connected. And you basically built your deck of cards, and you dropped it off on a counter, and then you went away for a while. And eventually it reappeared, now wrapped up in paper, telling you what you did wrong and why it wasn't going to compute for you. So from there, I went to Cornell and really dug into computers as part of a professional activity. So we were engaged in applied material science, I guess you would call it. And one of the tools that we used, so we would synthesize things, you'd get little tiny crystals, and then you'd solve the crystal for its molecular structure. I'm going to show you a few. And you do that on a computer. So the IBM 360 is now up to an IBM 370, but we had really state-of-the-art computers that were, again, those screens with keyboards, and you know, they had storage in them that you could go away and come back, and it would still have the stuff. You didn't have to load it in every day. But so I'm engaged on a regular basis doing chemistry inside glassware that looks like this. You'd attach it with hoses to a manifold that looks like this so you could keep the air out. The things that we worked with had metals bonded to other metals. And all of you, I'm sure, know something about organic chemistry and that it's formed of chains of carbon compounds, and a lot of them are very stable, and we're based on them. Metals don't like to bond to metals in molecules, and so you have to protect them. And this is how you do it. You synthesize them in here, and then you take these vessels and you put them in this vacuum chamber, and you get them into this glove box, which you've probably seen someplace. And so now you're in the gloves, and of course, we had large gloves. They were like extra large gloves because the professor who was operating our lab had big hands. And fortunately, my hands aren't small, but you're wearing cotton gloves and rubber gloves, and looking through, you can't see it in this picture, but there's a microscope on a stand outside that's looking through the glass, and you're, with these gloves, trying to pick up a crystal that you can just about see with your naked eye. It's smaller than a millimeter on an edge. And you're going to stick it on the end of a glass fiber and slide that into a glass capillary and bring it out and seal it off, because it's got to be under argon. If you let it be exposed to air, then it dies. So you take your crystal out, and well, what do crystals do with X-rays? They diffract them. And it's analogous to reflection. So if you have X-rays coming in, they bounce off the planes of atoms. And I'm going to show you some other things that help you think about these in 3D. But suffice to say that at certain angles, the X-rays that come in and hit the first plane will be one wavelength ahead of the X-rays that come in and hit the second plane. And so at certain angles, they come out in phase, so they're coming in like this, and then they bounce and they're coming out like this. And because the peaks are together, you get spots, and you can pick them up on a film, or preferably in a diffractometer. And this is actually the model of the one that I used back in, 1981. And so in the center of this stuff, the crystal is sticking up on this little fiber, and that's a 4-circle thing that cranks around, and it can position the crystal any way you want, and it knows how to do it. You don't have to tell it all the spots. And it's got X-rays coming in, and it's got a detector. And instead of getting a picture that looks like this, you get a whole bunch of numbers. The spot was this bright, it was this wide, it was at this position. And this instrument writes it onto magnetic tape in a device like this, and then, this is SneakerNet. You take the tape, and you go, down 6 flights and across to the next building, and you plug it into another tape drive that looks like this, and you read it in, and now you've got it in the computer. And so then this is what comes out. These are molybdenum dimers. So I've got molybdenum, I've got sulfur is yellow, I've got phosphorus is orange, and then I've got gray carbon. Hydrogen's not shown. And so it's in a repeating pattern that has that shape. And the other corner of this box, it's called a unit cell, has another version of it. And you say, because it looks so empty, right? But it isn't really, because there's 2 of them in there. And the atoms are really bigger. They look like this, and so there's 2 of them that are touching, and then you can see where they stick out. Well, they're sticking into the next cell, and something just like it is sticking into the cell on the other side. So 3-dimensionally filling space. So here it is again, and what I'm going to show you in the one on the left is that the 2 molybdenum atoms there have 2 of these guys that make a little 4-membered ring, those 2, and 2 that make a 5-membered ring. These are bridging, and these are chelating. Now, my wife asked me, why did you do this? And so, I'm faced with justifying that I was just getting an education, right? But somebody was paying me to do this. And so what we were trying to do with these was get them lined up. So the idea was that if you could get a bunch of these in their crystals and they're all pointing at each other, that you could get all of the metals to be in a long chain. And there are such compounds, and that was the other half of my thesis that we're not talking about today. But you know, this isn't going to work. The ends are blocked up. And so my goal was to try to figure out how to get all of these ligands to be bridging, like that one. And so you can see that one has exposed ends, and in fact, it even grabs something else. And this is very common in crystals, that was some solvent. That was some of the liquid that the crystal grew out of. And so that red oxygen is actually touching the molybdenum and making it happier, which was what was trying to happen in the other one. These were a couple other structures that I did, and in this case, red's oxygen, the blue here, that's a zinc, and this is an iron, and it's got a bunch of organic stuff around it, and there's like 52 atoms in there. And, okay, so that one clearly we did for fun. And this one is a very similar thing where it's all the same elements, only now there's 3 irons around the zinc. Well, that makes that have a negative charge, and then this guy over here is an ammonium ion. It's a positive charge, think sodium chloride. And I know that some of you are saying, why is there so much chemistry? All right, so we'll move to a different range. So I'll just make a little point on that. Each of those crystal structures cost me in excess of 100 hours of time, actual time, and it cost you know, the computational, the calendar, probably closer to 2 months. You know, so you see 4 of them there, and I've kind of made the point in the past that a face-to-face PhD takes a long time. It's just a lot of things that go on that are not coursework. It's a busy activity. All right, so I left academia the first time and went into industry, ended up working for 5 different companies in one place. We got bought and sold through the 80s, so 23 years I was there. But very early on, the IBM PC appeared, and well, there it is. I don't know, how many of you are, yeah. So yeah, you've all experienced one. Many of you own one. This is the earliest one, right? Floppy drives. So those tapes I showed you were 5 to 120 megabytes. Right, these guys were what, 360K? So much smaller storage. So the first one was purchased in my group. I was part of that. We were so excited. You know, it was like $5,000 for this little box. And we justified it saying we needed to do literature research, which of course we did, but we really just wanted to get our hands on one because we wanted to do computer data acquisition and cool slides and graphs and things like that. And they started to proliferate slowly in the lab. And then one day, the managers discovered that there was a program with which you could make slides that looked sort of like this. They didn't look like this, but from Harvard Graphics. And then all of a sudden, everybody in the building had to have their own PC, and it became much easier after that. Along the way, because I was working with them a lot, I was using them to do molecular presentations, we'll say, like the things that I just showed you, where we were trying to, again, build materials, now more organic materials, and it was useful to think about what their structures would be, and there were becoming programs that could do that. This was just, at this point, for viewing, to show things. But apparently, I was the most obvious candidate when our Dutch parent, so I joined an American company, but then it was bought and sold, and eventually this company, OXO, owned us, that had a large computing operation, said, well, we need to do that in the US at our research center, and lucky me, I got picked. I mean, it really was just a huge opportunity. And you know, before you know it, I'm spending hundreds of thousands of dollars to buy computers and software and learning to do molecular modeling, the real thing. in the meantime, the family is going into the veterinary business, and so as a sideline, I'm using the PC that I have at home to learn something about accounting, which then ended up paying off in that knowledge allowed me to write a chemical inventory system that went back and did in the research center. So, what does this computational chemistry look like? It's really at two levels, and so at the lowest level we have quantum mechanics, in which electrons that behave as waves. So that's the depiction of an electron, and it's swimming through space. It's not attached to an atom. But when you put it close to a nucleus, it has to wave its way back and forth. It's got to bang back and forth in a box, particle in a box. And so all of these people participated in various ways to produce software which, come to find, anybody can download and run. And at the time you had to again pay large amounts of money to be able to license these things, but today you can just download software that is extremely sophisticated. And I'm going to show you some of the things that it can do. And one of the things that it does, which will lead into the second half of the modeling, is that it helps you understand the physics behind the way large systems work. So here's an atom, and it's got, you all see that's a 1s orbital, right? Some of you see that's a 1s orbital. It's spherical, and it's close in. The nucleus is not that big, but if we colored the nucleus the size that it would be, it would be uber tiny. It's like a baseball on the pitcher's mound in an atom that's the size of center field, right? That's the nucleus. So obviously they don't do it that size. And then there's so there it is, and it's just it's going to rotate around, and this is going to cycle through some orbitals, and I'll just tell you. So this is a 2s orbital. It's bigger, and then once you get to the 2 level, you're allowed to have other symmetries. And so you can have p orbitals. There's 3 of them. They have lobes that go in different directions. Some of you remember this. And then there's other shapes that come after that. But what happens is atoms get together and they overlap. So here's a carbon monoxide molecule. Oxygen's on the right. And here's some of the orbitals that hold it together. And there's pairs of those atomic orbitals. And they're overlapping. Oh, look, those 2 p orbitals. And they're side to side. That's a pi bond. There's another pi bond. That makes it a double bond or a triple bond. This is what the molecule looks like from the outside. So the yellow is the oxygen, and it's more negative, and the other side was the more positive side. Just showing you some things that you don't have to worry about later. Here's an ethylene molecule, and again, you see that it's got all these orbitals that connect in various ways, but because of those ones that cut across or cut along, it won't rotate freely around the center. Remember that, because it's going to be important in just a moment. So here's what ethylene looks like. And again, you see it's got a negative aspect and a more positive aspect. And that's the way molecules look to each other. They're just big pillows with like, parts that stick to different other things. Another thing, just because I'm here on quantum mechanics, that you can do with quantum mechanics is chemical reactions. So here's a bromomethane, and it's reacting with a chlorine to become a chloromethane. And this can be computed with high accuracy that matches experiment, and it's used to predict the kinds of reactions that should be possible, how we should do them, what kind of catalyst might work, and what have you. So, and you can do it at home. All right, so that's enough quantum mechanics. What I spent most of my time doing in industry was called molecular mechanics, where we take collections of molecules that can't do reactions. The bond, whatever they are, they can't break bonds. They can just go around these pillows, and they can do whatever motions they have, and I'll show you some. And they can stick to each other or push each other away. They can do whatever their energy allows them to do. It's based on molecular mechanics. It's called molecular dynamics. And I'm going to show you some dynamics. And obviously these are the molecular mechanics over here. And again, there's incredible open source software. Well, it's not really, it's open source, it's free to use, not necessarily to reuse. And what I like to do with it is take a collection of molecules and put them in a box, and then shake the box and see how big it wants to be. I'll explain more about that. But we see how big it wants to be at a given temperature, so what do? We have a thermostat, we have a way to check its temperature, and if it's getting too warm, we drain a little energy. If it's getting too cold, we add a little energy. Check its pressure. How hard is the box pushing on the box next to it? So it's got a thermostat and a barostat. And it lets you do a variety of fun things. So molecular mechanics is based on a force field. Force field just means that we have our masses, those are the atoms, and they have some kind of function that causes them to be attracted to each other or repelled from each other. They're going to want to stay typically at some distance. And I'm going to show you some pictures of the way that they stay at a length, the way they stay at an angle, and the way they rotate or do not. So remember that earlier picture I told you about. And then that's going to let them exercise, do whatever they do, and then each one of them is going to be swimming around in its box, and it's going to be bumping into other molecules, and it's going to have surfaces that have ends that likes to stick together and ends that want to stay apart. And if we're lucky, we'll be able to take this box and predict the density of whatever these materials would be. That is, does it float on water or does it sink? That's what we mean by density. All right, so this is from quantum mechanics, and this is a stretching vibration. So this is really, if you look with the correct light at a carbon monoxide molecule, you'll see that it does this. It vibrates with a certain frequency, certain energy. All right, that's a CO2 molecule, and you can see it wants to be linear, but it bends back and forth, so that's a two-center. This is the nitrogen dioxide. It wants to have 120 degree, but it's going to vibrate back and forth. And then the last one is the four-center. So anytime I have a single bond, I can rotate around it. This is how proteins fold. They coil up and they wrap around themselves. But this is that ethylene molecule, and it can't rotate all the way around because it's got bonds that prevent it from doing that. So it wants to stay flat, but it can still oscillate, and so it can come to different shapes. And all of this comes down to, a little bit of mathematics. So there's a function. There's a function that mimics what they really have, which is that if I have an atom here and another atom here, that's like these guys, they're R apart, then if they're somewhere on an energy level, they oscillate back and forth that far. And they do the same thing whatever level they're at, and they usually only experience some low levels. This is a complicated function. This is a nice parabola. That's y equals x squared. And so we use a harmonic instead of the real thing, but it does a pretty good job. And so there's just math that's in the computer. And it's like that for all of those interactions. So whether I'm doing a bend or a rotation, it's just an up and down kind of thing. How about the stickiness? How about the molecules that come together? Well, all molecules have at least a small attraction when they touch another molecule. It's called dispersion or van der Waals. And it looks like this. So that when they're too close together, they push apart. So that's going up the hill, so I'm pushing apart. When they're far apart, they feel no attraction. This is the force of attraction or repulsion. Attraction is down, repulsion is up. And then there's a point where if they happen to be at that distance, they'll just kind of hang on. But then if they get bounced away, then they'll have to do that with somebody else, right? So they're all just going to be swimming around, and they can do that. They all have it. It's relatively weak compared to the electrostatic interactions. And so these are like charges repel and opposite charges attract. And so when two molecules come together, they say, okay, you have a positive end, I have a negative end, those are the ends that we're going to point at each other. You go the other way, and then we're going to push apart a little bit. It's just the way electrostatics work. And so these are actually two different functions, and it just depends on whether the charge is opposite, and then you get attraction. The same, you get repulsion. So we got all of this math. It's in a chunk of software, and we're going to build a molecule, and then I'm going to make a bunch of molecules that look like that, and put them in a box, which is, again, just math, to say that everybody in the box, you have your reflections in the box all around, and then we're going to shake them up. And there's going to be a variety of different organic compounds that we're going to do. So I'm going to make one, I'm going to make a line, I'm going to turn the line into a plane, I'm going to turn the plane into a cube, make a little adjustment to make it really cubic, and so it's going to look like this. So there's an ethanol molecule, right? This is the one you all wish you were drinking right now. And there's 5 of them in a line. And then there's 6 5s. And then there's 5 of those. And there they are. So they're in a cube, and it does look like the Bohr cube, right? Anyone seen the Bohr cube? Wow, I'm dating myself with Star Trek? Okay, I guess so. So yeah, so there they are, and nothing's happened yet, right? I just built it. So went through a script, and I built this thing. And then what we're going to do is we're going to compute from where everybody is, what is your force field telling you to do? And by everybody, I mean every atom, every single atom. And so they're going to do whatever their attached atoms in their molecule are, I'm being attracted, I'm being repelled, depending on whether I'm too close or too far away. Because if you're bonded, you can't escape. But then all the molecules that are neighbors or even next neighbors are feeling these other forces. And if they're neighbors, they're feeling those dispersion forces, and they're trying to stay together, just not too close. They're going to bounce off if they get too close. And then the further away, they're also going to feel these electrostatic effects. So if there's some negative and positive charge out there, it's going to push or pull whoever the species are. I've probably run 1,000 of these in the last 5 years, maybe more, I don't know. I just lost track. So, I build a box and then tell it to equilibrate, shake yourself around and you see there 500,000 calculations. The calculation is a femtosecond, which is what? So there's milli, micro, nano, pico, femto, 10 to the minus 15th seconds. And I'm going to run that, 500,000 steps just before I get started, just to make sure everybody's relaxed, equilibrated. I'm going to run it for 1,000,000 steps. That's a nanosecond. So the whole data set is 1 nanosecond. And it takes a week. It takes 4 days to a week. For several summers, I would have 8 or so of the chemistry department laptops sitting out on benches, up until the power died or something like that. And I go away and I come back and feed them new things to do and keep them busy. And so I've run 20, 23, 24 compounds, 25, at all different kinds of temperatures. And those are the data that I'm going to show you. So first, this is my ethanol molecule, and now he's relaxed. Right? So it's that same box, or one like it at least. And you can tell it's still sort of cubic, right? But some of these guys might actually be dangling over the edge into the next box. And you're going to see that when it vibrates around, that they flick in and out off the edges. And if you get all the way out of your box, then you get picked up and put in the other side and stuffed back in. Say, no, you can't go away, but you get it come in as your mirror image. And so that's what's happening when you see them flicking in and out. These are 1,000, those are 1,000 femtoseconds apart, so those are a picosecond. And so they're just like really lots of motion between them. So that was ethanol, and just to show you, this is cresol, which is, it's an aromatic, so I don't have more context for you, but you can see it also has that OH that makes an alcohol, and it's flat. See how they're flat? It's got this flat ring, and that thing's going to stay flat. It's just going to flex a little bit, and so then these things. Now I've got this spinning while it goes, just so you can see that it's staying more or less cubic, but you can also see that they're kind of jumping in and out. They don't look as active as the other ones were because they just don't have as much freedom of motion individually. So they're more just jumping around, and this is much more on the molecules interacting with other molecules side of things. All right, so here's some data. These are, so where's ethanol? And I'm not going to show you all of these in any gruesome detail, but here's ethanol. So this green line here and these green spots, the spots are my simulation. The green line is what you get if you go to the National Institute of Standards and Technology and they see these are the data for ethanol. This is actually one of the nicest sets here in terms of them all looking good. Other compounds, you can see that these are all at densities that are lower than experimental, as are these. These are species you might find in gasoline, so they only have dispersion, no electrostatics. These are acids. This guy is acetic acid, that's vinegar. This is formic acid, and it's one of only two that came out with a higher density. Here's the cresol that I showed you, that's the green one, and then phenol just differs by a carbon and 3 hydrogens. Here's a bunch of things that don't have alcohols that are just like these, so more of those flat molecules. Doesn't really matter. Here's all the data. Here's 25 compounds. The straight line is slope 1. So that's where, if you're on the line, then the simulation matched experiment. And it's actually, pretty impressive. Here's the group of alcohols, the first group that I showed you. Cresol and phenol. Here's the other species that were on the same page as that. There's that formic acid way up there. I mean, it is really dense, and it just came out that it was a little denser. Acetic acid is way down here, so they're all across the map, but they're within several percent of what you'd expect. And so this isn't a great thing that I did. This is the force field is that good, and it's the amoeba force field that comes with Tinker, that if you build these things, they will come, right? They will display their properties. So anyhow, I like it. I hope you do. Water. Oh, I didn't. So where's water? Here's water. Water is really close. They put extra effort into water. Water, you all know, is the most special molecule on Earth, and without it, life would be impossible. There's a number of reasons for that, but one of the really significant ones is that ice forms in the top. Most substances freeze from the bottom up because the solid is more dense than the liquid. Water is densest at 4 degrees centigrade, 4 degrees above its freezing point. So it gets denser and denser and denser as it gets cold, and then it gets less dense as it freezes, and so the ice floats. And otherwise, all that stuff that was evolving on the bottom of the ponds would have been dead. It would have just, would have froze, and I don't think we'd be here. So this is water, and they put extra effort into it, and I'm not going to claim that I really quite get the 4 degree peak, but it really does get the shape that it should have, and it's close all the way. This is 0, 273 kelvins. That's 0. And that's 100 centigrade, right? 32 and 212. I don't know if we have any Fahrenheit speakers, but it does it does a heck of a job, no two ways about it. All right, so, you know, here we are at college, and if I'm doing professional things, well, some of them presumably are going into teaching. And the molecular orbitals and the atomic orbitals that I showed you, you know, I trot out every fall and spring in Gen Chem 1 and say, here's the real orbitals, and they're spinning around, and I don't know if they like it or not, but they have to look at it. I've had a few other connections with computers and students. Some of you remember Josh Allen, and one of the things that I've always been fascinated with, and because you heard about it way back at the early days of Stauffer, is connecting computers to instruments and, you know, using it to pull the data. Why am I typing this in? You know, why am I not just collecting it and I get more of it and I get it faster, I get it better, whatever. And so Josh did some of that. Jenna Lee McFadden did, in a sense, an extension of that. There are these little tiny single board computers. There's a whole bunch of them, but the one that she used was an Arduino. Some of you might have also heard of Raspberry Pis. There's a bunch of these things you can get at, you know, $10, and they connect to the world, and they can do things and send it back to you. And so she did something with that. Carolyn Davern, I was able to entice to do some quantum mechanics for a student science symposium, and I think chemistry didn't win that year, but I'm sure she at least got second. And Ivan Kochman did an honors project that some of you will have seen a couple of years back when he reported it. And he learned how to program the Python to be able to do that by taking a special course with me. I didn't do anything to help or hinder Katie Tyson, but on the eve of getting a sabbatical, I went to her honors presentation, and it was just like the coolest thing ever for me that she did this really fun math that I'm going to explain to you, and I'm going to show you how it looks. And so it was an idea that Brent had come up with, and she executed. And the idea is that you take a function, like, so, you know, think back that harmonic function, the parabola, and at any point it has a slope. So you can take a line and stick it on and make it a tangent at that point. And so the clever idea is, well, what if you take two functions, and that for each value of x as you run across, you say, where's the tangent of function f, and where's the tangent of function g, and where do they intersect? Because two lines only intersect at one point, if they intersect at all. So if f and g are two functions, then we're computing a new function, this intersection, big G. And there's nothing you can write down. You know, there's no algebra that you can say what the function is that produces this other picture. It's a parametric function, and it can only be produced by executing some steps. And so, you know, here I am on the beginning of my sabbatical. I said, I can do anything I want. And I was just, like, my head was still buzzing from seeing her presentation. And so I said, I'm going to program her thesis and make it general and see what I can do with it, just because it's there. And so I did that, and for her equations, she has, all right, so this is y equals x squared. And you say, why is it so flat? It should be pointing up like this. It should look something like this. Well, it's because it's plotted along with a cubic with y equals x cubed and some other stuff that comes after it. And that goes up much more steeply. So if they're going to be on the same graph, x squared is very shallow. So then all we're going to do, I'm not going to talk about all of the plots here, is we're going to run a tangent, say here, and if it's tangent at that point, then another one is tangent at this point, and well, they probably intersect in there someplace. So this is f and g, and this is big G. And these these two graphs and two of those graphs she had in her presentation. And so that's the first part of it. And you say, you know, I'm trying to wrap my head around this. And I was trying to wrap my head around it for the first half of her talk, and I finally kind of got it. So I'm very sympathetic if you're still wondering what I'm talking about. Everything's on this one graph. So you can see that the red, that's y equals x squared. The blue is the cubic. So it's that expanded, but it's got an x cubed term in it. And it's a little bit off center from where the y is, from where the x squared is. And then these are the tangents when they're way off on the left side. And you can see they must be intersecting off the screen. And so somewhere off the screen is G. Here's G. And G is colored such that it goes from blue to yellow in X. Because it's not, yeah, it's plotted on an XY, but it has a path that zigzags back and forth. It's not a monotonic function. And so I'm going to animate that for you. So the tangents are going to move, and where they're intersecting, they're showing you G. And as they swing down here through the bottom, the intersection shoots off to the right, comes back from the left. It did it faster than I could say it, and then it eventually heads off to the top. You need to see it again?
Yes, please.
I don't know if I can do it. I have to back up. And, yeah, and then it'll probably do it when I come back in. All right, so it's tracing down, it shoots out to the right, it comes back after it shoots out from the right, they reconnect on this side, and then it trails off the top. And I felt like the animation actually makes it really easy to see compared to trying to, so now you could probably all have it, and you get it in about 10 seconds because of the animation. So animation is a wonderful tool. I said it was general, and so the functions here are that same cubic. So I just started playing with it, doing other functions, and then x sine x. And so we've got one function that's like a sine wave, but it gets bigger as it gets further out. So there's also multiplied by x. And then the other function is the cubic. And then again, G is going to be this dark thing, and then it's going to head out as that yellow thing. It's zigzagging back and forth. And then it rolls over, and it goes out the other way. Python is like the coolest thing ever. So, yeah, I have to leave the slide. It was worth it, right? I mean, so I'm not done, but I'm just about done with everything that's not Wesleyan, and the Wesleyan will go quick, as I promised. All right, so that's the end of that. There's basically two things that I've played with in terms of Wesleyan data. One is an old hobby that goes back to the middle of the Jim Gray era, and it's just looking at the 990s that are published and available for all nonprofits, and you can either go to websites like these guys, and a year after they get filed, they eventually get published as a scanned PDF. Or if you're comfortable with XML, they all get published, and so it's by the IRS, but it's hosted by Amazon Web Services, and it comes down as like this dictionary file. It's just, it's got a label and a number, or a label and a word, and whatever. And so I've used all of these, but all of the data that I have, which is just 2 slides, is hand transcribed. It all comes from things that I started collecting a long time ago and typing in. And it's where some of our money goes. And I'm just gonna highlight. This is the beginning of the Clark era. That makes this the beginning of gray area, and then Stan Kane, and then Newbold goes back off the page in terms of who the president is. So Evan's not the blue thing there. And I'm not going to walk you through it other than to say that it has a relentless climb, and it climbs faster than, well, any other salary expense on campus, I think. Feel free to correct me. And, you know, then of course there was a big change here at the end of 2018, and the next year is in prep, and you know, it'll get filed sometime next year and it'll reappear. And it wouldn't actually be, well, particularly concerning, except that during the Clark era, he was fond of taking individuals and boosting them up over the threshold where they get reported on the 990. And so all the new marks, they all appear from here. So things like former president and what have you continue through, and so yeah, a bunch of these stripes don't continue, but a bunch of them do continue. And I like 2% as well as the next guy, but we're a good 15 or 20% behind in faculty. We're not really participating in this party, and it's not the fault of the current administration. So it's not, but it's something that the current administration can fix. All right, so the thing that I got intrigued with a couple of years back was I had not been aware that in 2016 the SAT rescaled, and I guess they do this, you know, every decade or so. And what they do is they want all of the test takers to be evenly distributed across the 400 to 1600 or the 200 to 800 range. They want the same. They want it. If you do a histogram, if you do population versus score, they want it to be flat. Mm-hmm. They don't want a Gaussian distribution. They want to spread everybody out. And so in 2016, the performance had skewed to the point that it was time to reestablish the scores, and so, you know, as before, this is the slope equals 1 line, and the red dots are the 2016 score versus what that performance in terms of questions answered right and wrong would have gotten you in 2005. And, you know, by the time you get up to 600, it's boosted 100 points, and then it sort of slowly comes back down. Obviously, the ends still have to be pinned. 400 and 800 are the edges, so, you know, it sort of looks like a bow. So I got interested in this because there was a brief moment where it looked like the enrollment and administration arms were going to run with the fact that our SATs went up by 100 points. Because it was like some of you remember this, it was like this little announcement. And then the news got in there, and unlike some other people in the more public sphere, I think the president said, no, we're not going to just lie that blatantly. And so the thing went away. So I was just curious to see, you know, what's going on here, what's going on with our SAT scores, and some of you know that, well, nothing really. They're not really worse because of this in terms of students that come in. But I went to pursue data to just try and understand this, and then I found myself apparently embarked on something that Jared signed up to do for real, and so we crossed paths in the middle of the summer. That he was asking people for data, and you know, Candy or whoever was saying, well, yeah, George Whitwell was asking for that, and so he rang me up, and we've communicated a little bit, and he's seen some of these things. It's not like there's going to be any surprises, but you know, I'm not really trying to do his job, and rather just, you know, kind of want to play with data, because that's what I like to do. I like to make pretty pictures. No animations. So, you know, here's the, it's a little imperfect, but here's the SAT scores versus year. And one of the big imperfections is this particular plot, I wrestled, and you can't imagine how long I tried to fix those years. The numbers are right. Until you get down on this end, the numbers are right, but they're just not year numbers. So they really are, out here, this really is 2020, and then these are entrance years, but these are like, that's like 98 and 96, and that's, you know, was the fact that it wasn't continuous. The red is the average for the year, and no, I don't know why that one didn't print. But you can see that it's pretty steady, and you're saying, yeah, but didn't the scores go up 100? Well, this is a normalized SAT. So I take all of the SATs, and if they're a 2016, I use that function and I normalize them back to what they would have been in 2005. And in fact, if they're an ACT, there's a curve that does that for ACT. So it's all of the test scores, all on one thing. And this looks really like yours, I believe, except that you probably pulled those out, and clearly nobody got 1800. So so there's a little spurious data in there, and it's, you know, one of the things that Jared's worked more on than I have, and I haven't tried to get any benefit from what he's done for that. Well, we're probably not going to get as many SATs in the future because they're not going to be taking SATs. What's a good proxy? Well, high school GPA is something that they're still going to be giving us, and you know, no, I don't have the stats for this, but you know, you can see that it's a big standard deviation. However, there's really a line in there, and there's some correlation. I break the data set, and I should just say there's like 4,500 total students in a data set that runs from 2008 to 2020, from whom about 1331, I guess, have graduated. And so when I use students, then this is all of the data. And you know, so these are spurious. Obviously, they got a 0 instead of not having a value, which they should have had for the GPA. Same thing here for the normalized SAT. If we go to if we go to looking at how the SAT matches with career GPA, well, if it's just all the students, yeah, maybe there's a line in there, but you know, it's not very trendy. If you pull it out for students that actually graduated, so now here's, and it's fewer than 1331 because we don't have SATs for everybody. It's just, you know, it's just people we have these values for. Yeah, you know, maybe there's a little trend, but not that much of a trend. So, you know, I think in terms, so maybe dispensing with it, at least in terms of expectation of what they're going to do for GPA, if we care about that metric, isn't going to bother us. Right? It's not really going to make a difference. We still have to decide whether they're ready for college, ready for Wesleyan. There's just a couple other things that I'm going to go through. And so here's a busy slide. So I haven't done a lot of those XY. I poured myself into trying to do an image, and this tries to get at everything all in one place. And so it's a heat map, which means that the color is the Z value. And so that's mapped out over here. So here's GPA. And so you want to at least be, you know, that slate blue if you're hoping to graduate. And it just happens to be versus sports, and I'm not picking on sports. It's just that it's a nice way to spread things out. And there's other ways, and I'll show one or two others. And then these are majors. Well, majors turns out to be a complicated thing to plot because we have lots of double majors, and even a few triple majors. And so, you know, so and then there's all those combinations. So that's majors squared potentially, and it's something to work further through. But this is as far as I've gotten through it. So, you know, you really can't make too much of what's here. I'm gonna point at one row, which is, so this is all students, and one row up here is football, and they're not getting a lot of yellows, not even as many greens as we wish. And I think that's not a surprise. I think we're kind of familiar with too many of them come in and their football career doesn't take them where they want to go, and they end up not really getting over the hump to working their way through a program. On the bottom, so this is like the check. So these are all those same boxes, and it's the number of counts that went into the one above, because of course that matters. I mean, how many points made the data point? And anywhere you see a one, there's only one individual that is in that sport and major that's in this data set. Okay, so that's too much information to digest. We distill it down, and so two measures that we use are gender and ethnicity, and you know, these are things that are tracked by law, not because we're trying to manipulate in any way. And so these now are graduates. So these are people who are in that 1331, and so, you know, obviously their GPAs have to be above 2, and well, they're comfortably above 2. In general, counts on the bottom, mean GPA, and you know, we all knew it, the women are smarter. It's as simple as that. So, you know, I'm not ashamed to admit it. And there's other things that could be pulled out, and you know, one of them is that the internationals tend to be a strong academic group, so it's not a bad theme. Obviously, we're not going to be an international college, but the fact that we've benefited from those students, I'm pretty sure everybody here would agree. And yeah, in terms of counts, so mostly white, but close behind African American. And then we have some not reported. We're not actually pulling out ethnicity in terms of internationals, and I think those are some of the things that are hoped for in the future. So, gender versus sports, you know, it's another thing, and I'm not gonna walk you through it, but it's the kind of thing that can be done with this, and I've sort of tried to share with Jared. Okay, I've got a tool, and what's worth looking for. And then this is actually the last one, and so it's an interesting feature that the data as it comes from Scott Marsigli is an Excel spreadsheet that's like 20 pages. It's 20 sheets, and so each sheet is a term, and so here I am plotting how many terms somebody appears in versus their entrance year, and then their GPA, and just, you know, a few things that come out that they tend to improve their GPA the longer they persist. Well, that's good. And so these are all students, and then, but if they're graduates, if they don't get out in term 8, then they tend not to have a very good GPA. And I guess we probably might have some anecdotal experience with this, and you know, here's some evidence. Okay, well, I've used my time, so there's some of my work, some of where the software came from, and some people who provided information that I could share with you today. Thank you very much for coming and listening. And I would take questions. I don't know if I can answer them. Yes?
So I have a couple questions. On the last slide, when you were showing the visual relationships, did you get like a quantitative relationship? Did you do like an ANOVA or anything to test to see if one thing predicted another? Like, does duration in school predict?
No, but this is absolutely, I mean, you're talking to Jared's dream, and he and I have had some conversations, and I know what his plan is, and absolutely, it's a multivariate set.
Mm-hmm.
And so the logical thing to do is to do a multivariable analysis and see what the correlations are, see which things really matter. I've tried to pull some things out that are easy to digest. And ultimately today there's all these AI ways of getting at what's going on inside this, and so that's kind of where I'm thinking of going next, because I really want to learn some of those AI tools, and so I'm sort of hoping, well, maybe I can pull those two things together and I'll learn some things I didn't expect. I think Jared's probably going to do some more standard approaches with, as you say, ANOVAs and other multivariate analyses.
Can I ask you another question about the slide where you, like a little while ago, where you had like a linear projection of like the empirical data, and then your theoretical data with the molecule movement was a little bit below it, at least in the center. It looked like it was always about the same distance below. Do you think there's like, at least in the middle area, like when you got to the edges, it didn't match that pattern? Is there maybe some like aspect of the model that's missing that might be consistent between within that data range and the X?
Okay, so just to be clear, are you talking about the plot with the straight line and all of the spots?
Yeah.
And they're all dropped except for two. And
yeah.
well, no, one of them was right in the middle, and it was way far off the sediment, and then formic acid was way up at the dense end.
Yeah, like it feels like maybe the model is just missing something.
Yeah, so
interesting.
and here's the reason. The people who developed this software are trying to model biochemistry. And so everything they do is about, can I get my proteins to fold correctly, maintain a structure that makes sense, interact with water in a proper fashion, and that's what they've optimized for. And all of those other things, all those other molecules that I was able to make are incidental. They're things that they're just sort of these things that they tossed out along the way. They weren't looking for me to come along and do what I did. I just said, oh, here's a toolbox. I can build some things. And I have shared that with them. I'm sure they have no interest in refining the model to predict densities. One of the things that was on a slide that I didn't mention is that, why would I be interested in this? Well, solutions. So, and I still haven't done this, but take different molecules and put them together. You can do densities, but you can do energy things and look at, do they want to mix, do they not want to mix? And I'm pretty sure that it's good enough to do that, and intend at some point to go forward and do it. They're always refining their force field, and it's not released yet, but there's like the next generation, the amoeba that I showed you is, I think it's 15 or more years old, and so they've got like a whole new way of looking at the electrostatics, which is really key to the interactions, and so we'll see at some point in the near future. That'll probably become widely available, and then I'll just redo all of these.
But it's just interesting that they were all the same distance, or for the most part, from the, like it makes me wonder, is there some component?
Well, I think they're the same distance because they're close. Yeah, I don't think so, but I hear what you're looking for. Yeah.
So I have a question sort of related to that. So you're comparing the model to some kind of empirical standard, right, to see how it matches?
Yeah, well, experimental data that, is...
Right, so where did that come from? Is it just, has it been established by
the measurement.
repeated?
Measurement.
You
Chemists in the lab
right.
tediously making measurements, and then other people checking their work. I mean, the way science is published.
Established, accepted standard.
Yeah, the best available. So I said National Institute of Standards and Technology, which is, in this country at least, the repository of the best physical data available. A lot of the data is hard to find, and you might have noticed that some of the lines were short, and it's just, well, nobody's bothered to measure further than that. Some of the data may not be exactly correct. And until somebody comes around and remeasures it, so, you know, there's always the possibility that the model is better than the data, but I think it's not that likely. Yeah.
I've got one more question. if you want.
Sure.
Just, the graph that you showed that was looking at the average SATs by year, I noticed with 2020, I couldn't tell exactly where it was at, but it did seem to be above the other years. And I'm wondering if that has to do with that there are just fewer SATs that were submitted because they weren't required.
And the
those
good ones were.
who did submit it, those who did well.
Because it was
submitted.
high.
I noticed
Yeah.
that too.
Yeah, no, I think that's right. I think that's right, and I think you're getting at one of the requirements for doing that sort of an analysis is that you really can't do it quite the way I've shown you, to just stand back and see what things are. That you have to go in and look at what, you know, how did this happen? There were a few standout colors in some of those graphs, and then if you look down at the count, it's one individual. Well, you know, one individual when they're, who knows who that person was and why it was stand out for high or low results. Yeah. Well, I'm so glad to have been able to do this in person and that you were all able to come, and so thank you very much for listening.
Thank you for doing this.